Okay, it's time to go back to tutorial 7, question 2, where we're looking at non-homogeneous recurrence relations. And the reason this one is a non-homogeneous, you might remember from linear algebra, which was probably a couple of years ago now, that a homogeneous system of linear equations were where they were all equal to 0, and that's the same thing with these recurrence relations. Now this one is not equal to 0, so it's not homogeneous, it's non-homogeneous. And that's this 2 to the n here. On the left-hand side, we have our a sub n plus 1 and a sub n terms, which define our recurrence relation. But on the right-hand side, what we have is just a function in n, not any a values of our recurrence. So what we're going to do to start off with is ignore that 2 to the n just for a little while. I'm going to leave it highlighted so that we remember we haven't used it yet, because we are going to need to use it, obviously, or it wouldn't be given to us. What we're going to do and how we're going to try and solve this is we're going to think, okay, this is like the very most advanced algebra. We don't know what the recurrence relation is. Sorry, we do know what the recurrence relation is. We don't know what the solution is, but we do know that we could just call it a to the x, because we don't know what it is. We can take the auxiliary equation, which is 1 minus 2 to the x, and if we think about it this way, this on the left-hand side is an infinite equation. The a to the x is going to have ... at the end. But if we multiply it out, and if somehow we can simplify it using the information we haven't used yet, if we can get a finite expression on the right-hand side, which is my blob right here, right now, we could then divide that. We could divide both sides, in effect, by 1 minus 2x, which is also finite, and get a finite expression for a to the x, which is what we want. So that's what we're going to do. We're going to expand out the left-hand side, try and see if we can make it finite, and if we can, then we can solve and get it that way. So let's get rid of this stuff because we don't need it yet, and let's expand. We know we've got our auxiliary equation, and we'll just give this the most general form possible. It's just an infinite polynomial, or as I should call it by its real name, a power series. And then we'll expand it out, and we'll keep the coefficients together to make our lives a little easier. The only time we're going to get a constant is when a0 is multiplied by 1. We're going to get x terms when we multiply a1x by 1 and a0 by 2x, so that's negative 2 a0x. We're going to get x squared terms when we multiply a to the 2x squared by 1 and a1 to the x by 2x, so we get minus 2 to the a1x squared. And if you're good at pattern recognition, you can see a pattern coming up here already. And if you're not colorblind, and I apologize, I try not to use color for that reason. Okay, so now we're going to factor out, we're not going to factor, we're going to take the coefficients. Actually, a0 we know is 1. We know that from up here, so I'm just going to substitute that in. And now let's just factor the coefficients so we can see what's going on here. The x term looks like this, and the x squared terms look like this. You can see the pattern, and hopefully this looks familiar. Remember that highlighted part we had up at the top? These are all of the same form of a sub something minus 2a sub the thing before. So we can use our equation up here. Here we have a1 minus 2a to the 0, so n equals 0. So we know that this expression in the brackets is going to be equal to 2 to the 0. Here we have that n is 1, so we know this expression is going to be equal to 2 to the 1. And so I'll leave that there for now. You wouldn't bother putting that in when you were doing your work. But 2 to the 0 is just 1, so this is x. 2 to the x squared. 4 to the x cubed. Just your powers of 2. And now we're pretty close. We can actually get this into a finite expression. We're just going to look at the summation we're going to think about what we know about this series representation expansions and see if we can move it backwards. This 1 is going to get in our way, so let's take it out, and let's factor an x out so that we get something a little more familiar. There we go. That's going to be good. Because now we know that this is 1 plus x, and the stuff in the brackets is just 1 minus 2x inverted. Or we could write it this way. So now we have what we said we wanted. We have something on the right-hand side that's not an infinite progression. We've used the yellow highlighted stuff up above, and now we're at the point where we can say, excellent, this is a to the x times 1 minus 2 to the x, so a to the x must be equal to 1 plus x. Now let's do this just for fun. And the whole thing is divided by 1, so maybe that's not your idea of fun. So let's write it this way instead. 1 over 1 minus 2 to the x, that's the first part, and then now there are 2 of those, so it's squared, the one we had before and the one we have now. So we've solved it in the sense that we have a finite expression. We do want to be able to give it in the terms of a to the n, because that's what we started with. So a to the n, if we just, well, I guess let's do the generating function first. Sorry, it's Monday morning. 1 minus 2 to the x, so that's the sum from k 0 to infinity of 2 to the k x to the k. And this one is the sum from I to 0. We have both a 2 to the x, a 2 times x, and an exponent of 2. So we have to do, be consistent, use k here. Getting a little excited. We have to do both the k plus 1 and, which accounts for the exponent here. Let's highlight that for fun. So that comes from that, and 2 to the I, which comes from this 2 here, and then our x to the I plus 1. Ugh. Sorry, I'm getting mixed up with my i's and k's. It doesn't matter which you use as long as you're consistent. Sometimes you'll see k, sometimes I, sometimes even n, but we're using n out front, so I didn't want to use that here. And now if we want to turn that back into the, that's not an is going to be the coefficient of that. So we just pull out the 2 to the n, and over in the second term, n 2 to the n minus 1. So that's question 2.